In this lecture, we are going to take a careful look at molecular descriptors where the numbers we use in modeling actually come from, what they represent physically, and when they can be trusted. So, our goal here is not to memorize descriptor names, but to understand their origin. By the end of this lecture, you should be able to distinguish between quantities that are directly calculated from structure and those that are inferred by models, and recognize which descriptors are robust versus method dependent, and identify situations where over interpreting predicted values can lead to flawed conclusions. Um, before we discuss all these things, let's do a quick recap. In earlier lectures, we introduced core physicochemical descriptors like logP, logD, pKa, TPSA, and hydrogen bond counts. And we discussed how empirical rules like Lipinski and Weber use these quantities to define drug-like space. Today, our focus is a deeper question. Where do these numbers actually come from? Okay, so what we need to know here is not all molecular descriptors are created the same way. And it is useful to start with the most fundamental category. Category one describes the structural topology of the molecule. What you might think of as the hard facts of the molecular graph. So these include quantities like molecular weight, hydrogen bond donors and acceptors, rotatable bond count, heavy atom count, and polar surface area, for example. The source of these descriptors is the molecular structure itself, specifically the connectivity and atom types encoded in the molecular graph. So they are calculated exactly from a defined structure, such as a SMILES representation, using standard cheminformatics rules. Because of that, their reliability is high. These descriptors are deterministic. If the structure is defined correctly, the descriptor value is correct. They don't depend on training data, statistical inference, or empirical calibrations. Tools like RDKit, OpenEye, CDK may differ in implementation details, but within this category, the numbers are fundamentally properties of the structure, not predictions about behavior. Now, let's talk about theory-based estimates. So this second category includes descriptors like logP or molar refractivity that are estimated using established physical chemistry methods. So these values are not statistical predictions, and they're not measured experimentally here. Instead, they are calculated using defined procedures that map the molecular structure to an approximate um, physicochemical property. Um, because of that, the results are reproducible and usually reasonable for standard small molecules. However, their reliability depends on how closely the molecule fits the assumptions built into the method. When we move into unusual chemical space, such as metals, large macrocycles, or highly strained structures, those assumptions begin to break down, and the estimates become less reliable. Now let's see inferred properties. So, I mean, these other descriptors, including predicted pKa, predicted solubility, synthetic accessibility scores, or metrics like QED. So these are inferred rather than calculated. So these values are produced either by empirical models or by heuristic scoring systems. Their reliability depends strongly on the training data, the domain of applicability, and the assumptions embedded into the model. Importantly, when these inferred quantities are used as inputs to other models, so their uncertainty propagates forward. So that's what you need to keep an eye on. So this diagram shows how uncertainty accumulates as we move from structure to prediction. We begin with the molecular structure represented as a smile string. At this stage, there is no inherent uncertainty. The structure is simply defined. From that structure, we compute basic descriptors such as molecular weight, hydrogen bond donors, those kinds of things. So these calculations are deterministic. Given the same structure and method, the result is always the same. So their uncertainty is low. Uncertainty increases when we move to inferred descriptors such as predicted pKa or solubility or heuristic scores like synthetic accessibility. These values depend on models or rule systems and are therefore method and domain dependent. So when inferred when inferred descriptors are then used as inputs to a downstream model, shown here as a toxicity classifier, the uncertainty does not disappear. It propagates and can compound, limiting the reliability of the final prediction. Uh, Toxicity is shown here as just one example. In practice, the same uncertainty chaining behavior applies across other decision criteria such as efficacy, PK, developability, whatever the things we discussed in previous lectures. So to summarize, advanced descriptors allow us to reason beyond what we can directly measure, but they also carry the assumptions and limitations of the methods used to generate them. Many commonly used quantities such as pKa, solubility, synthetic accessibility scores. So these are inferred values rather than raw observables. So their meaning depends on provenance, the tool, version, training domain, and assumptions behind the calculation. So when models are chained together, uncertainty accumulates. You can easily imagine this, right? So downstream conclusions are therefore constrained by the reliability of upstream estimates. For reproducible and interpretable science, a descriptor generation should be treated as defined, documented step, not just a number pulled from a tool. Descriptors are powerful abstractions, but like all abstractions, they are only as trustworthy as our understanding of where they come from. Thank you.